The theory of relativity, the theory of evolution, the laws of thermodynamics. Science is known for being full of theories, laws, and explanations. After all, that is the goal of science, to understand, explain, master, and/or utilize the secrets of the world around us. But how does it happen? Scientists use a basic, flexible set of steps to learn about the world around them. This set of steps is called the scientific method. There are 5 commonly accepted basic steps. First, an observation is made or a question is raised. Then a possible explanation or hypothesis is proposed. An experiment is then designed to test the hypothesis. Data is collected, analyzed, and then conclusions are drawn. Okay, so I was trying to give a really good example to show you the scientific method, but instead of me describing an example to you, let me show you what happened to me a few days ago. Just watch this. Alright, let's get this lesson plan knocked out. Needs a little something. Oh, there you are. Hunter? Oh, baby, I'm coming. Hang on. Alright, hang on. 1, 2, there's that. Alright. I'll see you later, sweetheart. Get that lesson plan straightened out. Huh. Well, it's pretty. Don't think it would taste very even, but it's pretty. All the flavors just settling right down there at the bottom. Huh. That's better. Alright, let's get this knocked out. Honey, thank you for going to fill up the water pitcher. No, it's okay. I got some tap water. I'll fill it up in a minute. Alright. Here we go. Just get this. I'll take it. Hunter! Oh, baby! What have you done? Let me see. Alright, sweetheart. Oh, that's really pretty. Yep, that's a really nice drum, baby doll. Okay, well, let's go wash the markers off your hands. Alright, kiddo. Dry them off. Alright, Mom's gonna finish up her work stuff. There's it, sweetheart. Once again, I didn't stir it. And once is this different? This is definitely different. The color it is almost evenly distributed. That is pretty impressive. It's not at all like last time. You know what? This water was warmer. Last time I got it out of the fridge and the pitcher was empty today, and this is just a lot warmer. I wonder if that has anything to do with it. Wait a minute. Pause it right there. Look, I'm thinking. I made an observation that led to a question, and then I made an educated guess as to why I observed the dye and water interacting the way they did. My hypothesis is that the warmer water, it caused the dye to move around more because the particles of water are moving more, so that means the dye will be distributed more evenly quicker. In the cold water, the particles aren't moving as much, so the dye is not distributed as quickly. Now, I have an observation that there was a difference in the dye distribution between 2 glasses of water. And I have a hypothesis. I think the water temperature controls dye distribution. So, how can I prove this? How can I design an experiment to test my hypothesis. Okay, so now we need to spend some time talking about experimental design. Experimental design requires that we try to get rid of as many variables as we possibly can and pick just one to focus on. A variable is something that can be changed within an experiment. In this case, the variable we want to test is the temperature of the water. Now, if we use different amounts of water, different size containers to put them in, these could be additional variables, and we don't want that to happen. So, while we're designing an experiment, we need to keep in mind our materials list and make sure it allows us to only have one variable. In this case, we are going to need some glasses. Make sure the glasses are all the same size and will contain the same amount of water. To do that, you'll probably want to use a graduated cylinder. You will also need to use some food coloring. Use the same color in each glass. Use the same number of drops of food coloring. This decreases the number of variables, so we're only checking the water. Now, if we're going to test for water temperature, we will need to have a thermometer. You need to be able to tell what the temperature is. We're going to test one at room temperature, one that has been heated, and one that has been cooled. So make sure you have cold water on hand and a way to warm up some water, either a microwave with a microwave safe dish, or you could use a hot plate. Just make sure the water gets nice and warm, take the temperature, and you probably want to shoot for around 90 to 80 degrees Celsius. Now, as you design the experiment, it's going to be difficult if you don't have someone to work with you to put the water in the cup simultaneously. We won't be timing them. This will be very nice, exact, and it would give us some quantitative data, or data that is measured. We're going to take qualitative data, data that is observed. This is a bit more subjective, but for our purposes it will be fine. So, our qualitative data is going to be the relative quickness with which dye spreads through water of different temperatures. We're going to start off by putting dye in the cold water, then the warm, and then the hot in rapid succession. As I said, if I had enough hands or a partner, I would put the dye in all at once. However, as long as you start with the cold water, it's going to be pretty obvious what the results are. So, I set up the experiment. Let's take a look and see what happens. One more minor detail. When you design an experiment, it is important to write down every single step that you take. This way, your experiment could be replicated by yourself or another scientist. And why would this matter? We're only dealing with something right now that is well known, that water molecules move faster when water is warmer. If you were testing a new idea, more scientists would want to test it, so it could be peer-reviewed, so it would be backed up by multiple tests and could be taken as fact, or certainly a very strong theory. So, it is necessary to write down your steps. That way, someone can replicate your experiment, and it proves that you have been consistent and accurate in your scientific methods. The procedure should be the following steps. Step 1. Heat 350 milliliters of water for 150 seconds in the microwave. While the water is heating, you also need to cool 350 milliliters of water to approximately 40 degrees Celsius. Place 350 milliliters in each of the 3 glasses as follows. You need 350 milliliters of heated water in glass A, 350 milliliters of room temperature water in glass B, and 350 milliliters of cold water in glass C. Measure the temperature of water in each of the glasses and record your results. Then add 2 drops of food coloring, the same color, to each glass. It would be ideal to add these simultaneously, but if you are working alone, please do them in the following order. Add 2 drops of food coloring to the cold, then the room temperature, and then the hot water. Step 6. Carefully observe the movement of the food coloring through the water in each glass. Record your observations. Be certain to observe the relative speeds with which the food coloring disperses through the water in each glass. Step 7. Use your second color. Add 2 drops of food coloring to each glass as described in Step 5. Step 8. Carefully observe the movement of the food coloring through the water in each glass. Be certain to note the mixing of colors in the glass, whether or not the color plume is disrupted and dispersed, the relative speed with which the color in the glass becomes homogenized, all one color, and any other particular movements you notice in the water and the food coloring. Now that the experiment is complete, it is time to analyze the data that we have collected. This data collection and analysis is when you report and analyze the data that was collected. The analysis does not include an explanation or discussion of the results, but a statement of what was observed and of any statistical analyses that are run and graphs that are created. In this experiment, our data is qualitative or descriptive. We did not collect quantitative data, which is discrete and measurable. In many experiments, there is a measurable quantity to be analyzed. However, due to the nature of this discussion, I chose to use qualitative data instead of quantitative measurements, such as a time measurement. This could be done by setting a timer and noting how long it takes for the water in each glass to become fully colored. If you chose to do this, the warm water would need to be kept at a constant temperature on something like a hot plate, but it could not reach boiling. The cold water must be left sitting in the fridge, and the room temperature water should be left out, but not in direct sunlight or a draft that could alter its temperature. You would also need to keep a thermometer in each glass to monitor the temperature at all times. The data that we collected was as follows. Color dispersal was quickest in the hot water, then the room temperature, followed by the cold. Color mixing was also quickest in the hot water, then room temperature, also followed by cold. Mixing was incomplete in both the room temperature water and the cold water at the time that the experiment concluded. A plume of red food coloring going towards the bottom of the glass was still present in the cold water only. The room temperature water had swirled areas of color. The general color of the water was mixed, but not homogeneous. The hot water was a nearly homogeneous color at the time the experiment was concluded. This takes us to our conclusion. This is where the data is interpreted and explained. Be certain to relate this back to your original hypothesis. If the data supports your hypothesis, the hypothesis may undergo further testing to support it. If it does not support your hypothesis is rejected and a new hypothesis may be formed. For our conclusion, in short, our data supports our hypothesis. Water temperature was directly correlated with the rapid dispersal of color throughout a glass of water. As you increase the temperature, you increase the speed with which color disperses. The lack of movement of the water molecules in the cold glass was most apparent when the second color was added. At the end of the experiment, a red color plume was still clearly visible in the glass of cold water, but in the glass of hot water the color was homogeneous and no plume was visible. The water that was at room temperature was slightly tinted purple, as would be expected from mixing blue and red, and it was still possible to see swirls and patches of an even color, and even to watch these regions change and flow. The variations in color dispersal observed are most likely controlled by the movement of water molecules in each glass. It is a widely accepted fact that molecules at a lower temperature move less than those at a higher temperature. The increase in the motion of water particles, which correlates with an increased temperature, would explain why the food colored in the hot water became homogeneous most rapidly. Similarly, the fact that the color plume was still visible in the cold water supports the idea that the water molecules and dye molecules in the cold water moved very little from their initial positions when the food coloring was added over the course of our experiment. This supports the hypothesis that with an increase in temperature there will be an increase in the rate of food coloring dispersal in water. Now, if we wanted to spread this exciting news to the scientific community, how would we do it? Would we go to some bio Facebook page and make a proclamation about the law of watercolor swirls? No. We would want to publish our findings in a peer-reviewed journal. What does this mean? It means that we would write up a formal report of our experiment and ask other scientists in relevant fields to read the paper and make sure that our experiment was high in quality and truly supported our hypothesis. Science grows when scientists share their findings, and it is strengthened when good science is published. All scientists benefit from ensuring that only precise, accurate material becomes part of the body of scientific knowledge.